Let others join. We'll start this today's session. Yesterday we have looked at the architecture of the database management system. Few examples as well we have walked through. But once again, some students have asked me that since there is a interruptions, audio interruptions, to revisit the specific parts of the yesterday's lecture. So accordingly we'll take it forward. But before that, I wanted to just give you the pointers that for the next week's lab, you all are requested to install the MySQL and the installation related notes. The help files are all available at this particular place. Installation accepts, right? And then here you have the installations, how to install on Linux or Unix systems, how to install on Mac OS, how to install on Windows, and many other pointers are available. This is a clickable link, so you should be able to visit it without any issue. You are expected to have this MySQL installation on your machine for the upcoming lab. We'll see. I'll also kind of detail you the next week's lab is all about installing the MySQL alone, because we could not gather sufficient material to proceed with the next week's lab. As you all know, the next week's lab sessions syllabus is this week's 3 lectures, and this week's 3 lectures are all introductory in nature. Not able to introduce enough of the SQL things. So my expectation from the next class perspective is that you all have installed a MySQL version, latest version, which is up and running. That is what is the expectation of this particular thing. And then the material for this one is through this slide. So you should be able to install this one. And those who are using Ubuntu or Unix kind of systems, this installation is much more straightforward, and I assume that it is almost the same with respect to the other operating system flavors as well. So with that, I will proceed with one question one student has asked, that what is this memory constraints and what exactly going on over here in this particular example, or what are the details. So I just wanted to tell you that, let us say for a minute or for example, you have 6,000 student records. Say all the names of the 6,000 students, 6,000 students. This element can be anything. It could be name, it could be roll number, it could be department, it could be CPI. I am using a generic word, element, which is stored on the disk, which means that it is staying in a file. So I have 6,000 students information, and now the constraint that is bringing in is that assume that main memory can hold only 100 elements. It cannot hold all the 6,000 elements. So if you have the familiarity of interacting with the files, you can read the file, complete file into your main memory, provided your main memory allows it. Main memory has a size limit after all, right? So assume that the constraint is that you can only read 100 elements from the disk, which means that 100 elements from the file. So what is it that you do is that the objective is to make a simple sort of these elements. Sort the students' names by their names, first name. Sort the students' names by their last name, and so on and so forth. Or sort by roll number, sort by department, whatever it might be. Simple functionality of how to sort. If this were to be the case, we cannot definitely load all these 6000 records and invoke in-memory sorting algorithm. Once all these 6000 elements are loaded, you know how to sort them using in-memory sorting algorithms. By in-memory sorting algorithms, as you have all these 6000 elements on the main memory, you can apply any sorting algorithm. That is exactly what I mean. Because we do not have such a kind of flexibility of loading all the 6000 records, we take the records of the size main memory can allow us. If the main memory allows us 100 records to be read from the disk and then only can hold 100 records or 100 elements, we load all the 100 elements into the main memory, do the sorting, and then store the intermediate result onto the disk. Now you have only sorted 100 elements, not all the 6000 elements. What you do next? You do the same procedure. Once again, you take from 101 to 200 elements into the main memory, load them, sort them, write to the disk. So you continue this procedure. Next to 100 records, you load them into the main memory, 201 to 300, sort them, and then write the sorted records into the disk. And where you write, as of now it's an abstraction, it's somewhere you will write into the files. And you keep repeating till you exhaust all the 6000 elements. You please read this as 6000 elements. Maybe I have missed out that particular thing. Right? So essentially you will be sorting all the 6000 elements over here. And then, but the question is that, are all the 6000 elements sorted on the disk? The answer is no, because they are individually sorted, but together they are not in sorted order. So what is it that you do? You once again go through all these files together and then merge them and then write back onto the disk. That's how this particular things will work. Right? And in practice, the database systems will not assume that the data must reside on the main memory. That is the strength of the database systems. Right? Otherwise, what will happen is that you will be having petabytes of data, but your main memory size itself is very, very limited compared to your hard disk sizes or the disk storage structures. So what they do is that for every operation that you do, any operation, if it is not fitting into the main memory, the database management system knows that it must do several passes on this file to perform the task that you have specified. Over here, the task that is specified is to sort these elements, 6000 elements. Now it will go through 60 passes through these disk elements and write as many intermediate files as required, do the merging, and then write back the results. So it is a disk intensive operations that actually goes behind the scenes of the database management systems. And you will never run out of memory problems altogether. However, if you rely purely on main memory based techniques, algorithms, what will happen is that they sooner or later will run out of the memory and then say that, well, I cannot perform this functionality. But such kind of issues will not actually arise with respect to database management system. That is why I am saying that as the size increases on the size of the elements on which you have to perform operations, as the size increases, the challenges are that computationally they become very, very intensive, both disk operations as well as the IO operations in general, and then the computations on main memory. All of these things put together will put this database system on a huge workload. I hope this is clear. Any questions? Any questions? So voice is not clear, lots of noise. So I'll get a new microphone which actually has noise cancellation. Please once again continue, bear with me for some more time. By next week I should be able to sort this out. Any questions with respect to the size and challenges example that we have discussed?
Yes, sir, I have a doubt.
Yes, please go ahead.
Sir, since we are sorting 100 elements, but later on when we combine all them, though it is not necessary that all the elements, all the 6,000 elements will be sorted. Like in small pieces they are sorted, but overall they will not be sorted.
That is correct. So that is where this merge operation will come in. So the merge operation will comprehensively merge all the individually sorted elements, individually sorted disk files. Okay?
Yes, sir. Yes, sir.
Perfect. And we are actually discussing at a very black box level. The details, as you open up these systems related details, you will understand how the DBMS perform these tasks. Here, the operation happens to be sort, one operation. But there are several such operations on the files to be performed, and each of these things must be on disk. That must happen on disk. So you will learn many of the variants of the operations. Here in this example, yes, please go ahead.
So I had a doubt that where would merge operation be performed, on the disk or on the memory?
On the disk only, because you cannot fit on the memory, because you can fit only 100 elements.
So then why not sorting operation is also there on the disk?
Sorry?
So if I can perform merge operation on the disk, why can't I perform sorting algorithm, sorting operation on the disk?
You will also understand that disk operations are very expensive. You have to use main memory. See, if you don't use main memory altogether, you will lose on the performance. Okay? As much as possible, you have to load the elements onto the main memory, perform the task, and then write the intermediate results onto the disk. That is how optimally you will be utilizing all the resources that are available at the DBMS disposal.
Okay, sir.
Right? So that is where the strength of the DBMS comes. So the size and then the challenges associated with the challenges are this particular thing. So you always have to remember that any operation that we are actually discussing, you don't assume necessarily that they are on main memory. The straightforward thing will be that this cannot fit into the main memory, and then DBMS handles such kind of issues. Okay. So now, what are the elements the DBMS has, database management system has? If you look at the comprehensive architecture of the database management systems, DBMS we have seen is a collection of programs. It's a software, and it must interact with the users. It must interact with many stakeholders who are using this software. Who are the stakeholders? The web forms, right? So over here, one example is over here that AAMS web form is there. You have filled your login ID, you have filled your password. You press the sign in that okay, I have filled in my details. Now you please validate. That's exactly what you will do it. Now what will happen is that this form Maybe written in PHP, maybe written in Python, maybe written in HTML, maybe written in any other web-based programming language. But the web-based programming language is at the user's front. It is your Firefox, it is your Chrome. But this data is entire data of the student role, login ID and then password is available at IIT Guwahati academic sections office, right? Somewhere, we do not know exactly. So what it means is that this web browser should arrange to pack this entire operation as, okay, user has given the login ID and password. You convert them into some database query. Why? Because you have to authenticate whether this is a legitimate user and then he is eligible for entering into this system. So this particular form must convert this form into SQL query commands, SQL commands. So that's what actually happens. And it is for any application software that actually runs on top of the databases. So over here the system is there. On the top of databases you have developed a web interface for the users to interact with the database. So what happens is that here you have seen a university system database. You can at the same time assume that all the examples that we have talked about in the structured databases, all of them are web-based applications predominantly. So they convert all such kind of inputs given by the user to SQL commands. So web forms, when you finally fill the form and then finally go, it will be converted into SQL commands. So is the case with applications. It need not be, if you ask, is it always about web forms? No, the answer is no. There can be many other application forms that can exist independently of the web forms within the systems. For example, if you look at any of your Windows system or Mac system or Linux system, they all run many implicit softwares which interact with the databases. And the moment you modify their values, they will be written back to the disk and to the databases. But these inputs, when you say OK or next or whatever it might be, they finally convert into SQL commands because these applications must interact with the database. That is another form of the input. The third form of the input is that you directly interact with the database by invoking the command line prompts, command line arguments. Over here, this is a terminal on which you write the actual SQL commands. Now user is here, you are assuming that user do not know about SQL language, but here you demand that the user must know the SQL language. Otherwise these SQL interfaces cannot be invoked to interact with the database. So over here also another example of SQL interface. Over here it is the responsibility of the user to construct a valid SQL command or SQL query or SQL statement, whatever, they are all equivalent. So all these three interfaces converts everything into SQL command. So this is an example of the SQL statement. Once this SQL statement is emitted by these applications, different applications, now the job of the database system will start. So far it is only the application front ends that actually that are responsible for constructing the SQL query, SQL statement, right? So now once this SQL statement has been constructed, you please understand that this SQL statement may inherently have errors. They must be checked beforehand. So now we enter into actual business of the database system. Right? Once this SQL command is submitted to the database does construct, it takes SQL as input, SQL statement as input, and constructs a SQL query. No, it constructs a parse tree. It constructs a parse tree out of the SQL statement. This is the statement. The equivalent of the parse tree is this one. And why it must do that one? It is pretty much the same with any programming language. If you have written C program, you must give this program to the compiler. Compiler first will check whether it is syntactically correct or not. Right? It is semantically correct or not is a different issue, but syntactically correct or not is the first step. If there are syntax errors, it will first will straight away reject it. So once the parser does its job, saying that this SQL statement is syntactically correct, what will happen is that this parse-tree, this command is generated by the user, because these are from where they are emitting. It is emitting from either web forms or applications or SQL interfaces, and they may not be optimal in nature. So what actually does is that see, when I'm saying optimal, I'll just give you very briefly the example that you wanted to perform operation on two tables. You wanted to take intersection of two tables, or you want to take union of two tables. Say intersection. So what happens is that the database will understand that what is the size of this table 1 and what is the size of this table 2. It will first compute. So even though you know that table 1 intersection table 2 is equal to table 2 intersection table 1, but computationally one is faster than the other. So the database management system will apply several transformations on this parse tree. So let us say this is the parse tree that actually has been obtained. That I have the table, I have to perform this operation. I have another table, I have to combine these two tables to perform this operation and then perform this operation. So this is what has been given by the web forms. But now optimizer will figure out that, well, this is not the correct optimized fashion in which I should run, but instead this is the optimized fashion in which I should run. And these details will be discussed at a later stage. As of now, you assume that, let's say, at an abstract level, this is what is the job of the optimizer. So once this optimizer does, this is not the correct way of evaluation, this is the way of evaluation. Both of them will give you identical results. What is the meaning of identical results? So the query might be that give me all the students who have registered for course CS245. This query also gives all the students who have registered for CS245, and this query also gives all the students who have registered for CS245. Result-wise, there is no discrepancy, but the way in which you execute, one will execute faster, another execute will slow. And database management system always prefers a faster method of execution. So once optimizer does such kind of decisions, it is up to the order in which you have to perform these operations must be understood. So which operator I must evaluate first, followed by which operator I must evaluate, and so on and so forth. So that is the job of the operator evaluator within the database management system. So operator evaluator will say that on the table movie, I perform this operation first, followed by on the table stars in, I perform this operation. Then followed by I perform this operation on resulting two tables. Followed by I perform this operation on the resulting table. So this is the execution plan. That is what is being obtained by the operator evaluator. Once such a plan is constructed and then very clearly it is shown by the database to the database management system, executor will convert this parse tree into executable statements. So executable statements will be brought into picture, and then they will actually ask some more details. That whether any auxiliary structures are existing, can I use some indexing things? I mean, is there, for a minute, you assume that are there hash tables involved for roll number, query that involves roll number? Or is there a tree that is involved on the name of the column name of the student? and so on and so forth. Those are all the files and indexes. Because these are nothing but they will make your life faster. They will not do anything more than making your life, computational life faster. So it will actually look for whether there are indexes and file structures are there on the disk to perform each of these operations. I wanted to select some rows from the movie. So are there any indexes that are existing so that I can immediately pull these rows? So that is what it does. And then it will actually look for buffers, intermediate buffers. Because I told you that in the database system, the main premise is that the entire data cannot be loaded onto the main memory. So it will actually look for in the buffers if the data is available or not. If it is not available, it will ask for the disk manager to fetch the data from the disk. Only at the last stage, it will actually ask the disk manager to fetch the records from the data from the disk. So that is what is the main thing. And in between, these are the two side boxes are there. They are always be there. They are always be present. Why? Because databases will not assume that there are no uninterrupted power supply. If the power goes off, your command almost goes away. You are, let's say, in the middle of doing some operation. Let us say you are trying in the middle of doing this operation. And if the power goes away, the recovery manager will kick in and then say that, well, you have a computation which is half done. Either I must completely undo it or I must redo all your operation. Redo means the entire operation I must redo. That is what this recovery manager does. The transactions and lock manager, what they will do is that if two users are simultaneously trying to interact with, see, through web forms, two users are trying to book a ticket, they will generate identical query. That is one thing. But with the difference that this is customer 1 and this is customer 2. Identical queries are generated. But one of them must, let's say, be given permission to write onto the disk, not both of them simultaneously. So transaction manager will look after who should be given the opportunity first to write onto the disk. Then what will happen is that the log manager will log the other user not to be able to write on into the disk till the first user completes his transaction altogether. So such kind of arrangements will be performed by these transaction and lock managers. Put together, everyone will only then interact with the disk if the data is not available in the intermediate buffers, if the data is not available in the indexing structures, and so on and so forth. Right? So these are all about the architecture of the database management system. Any questions? Okay, if there are no questions, then we will. So in the first half of the, so somebody is asking a question saying that so one is asking how merging happens. So merging, that is exactly what I wanted to kind of request you, is that these details you will be learning at a later stage. And we will not discuss the details over here, but what I wanted to appreciate is that these records are locally sorted, but globally they are not sorted. Some sort of merge must be performed. Merging must be performed on the individual sorted lists. And that's where these disk-based operations will come into picture. And you will be learning about these mechanisms or these algorithms in the next phase when you open up the black box of database management system. And they are known as the external sorting algorithms. You will get to learn about that one. But as of now, for this particular example, you allow me to differ how merging does, how sorting happens, and so on and so forth. Sorting happens, so how sorting happens? In-memory sorting algorithm, you all know. Many of the sorting algorithms. You pick any of one of those algorithms, perform and then write to the disk. And you assume that some sorting mechanism is available which will perform the sort and then obtains you 6,000 records and then writes back. And somebody is asking what is an indexing structure? What is index structure? So I will just give you one example of the index structure. Is that hash table is the index structure. So if I have some 6,000 roll numbers, I wanted to search one roll number from in the disk that is there in the disk. I give you one roll number and ask that is this roll number a legitimate registered student. One thing that you can do is that you go to the disk and then ask this question that you go serially scan completely and then say that till you hit 6,000th element, you exhaust the linear search and then say, well, the student's roll number does not exist. Versus if you have a hash function, somebody gives you this roll number, you don't go to the disk first, you just hash it and then it will give you a physical address onto the disk and then immediately go out to that particular location onto the disk. So this indexing structure will allow you to access the physical memory addresses of the disks. That is one example. The second example is that if I give you let me say such kind of records, this is the row 1, this is the row 2, row 3, row 4, 5, 6, 7, 8. You have 6,000 rows. And then you ask this question that give me the records of Smith, student Smith is what you ask this question. If you do not have indexing structure, what you have to do is that you have to first of all go to the first physical address of the disk, pull this record, go to this location, this address location. This is also not available. You go to this address location and ask this question, is it Smith? No, the answer is no. Then well, you have to move back all the way back and then you have to come to this address location. And then you have to jump to this address location and ask this question that is this Smith? No. So you have to kind of repeat it. But instead, if you assume that all these are available in a B tree form, B plus tree form, in a tree form, these records and then their physical addresses. Then you ask to the tree this question that, hey tree, you please tell me whether Smith is there or not. Tree will give you that answer along with the physical address, and then you immediately jump to this physical address and then fetch this record. That is what is all about the indexing structure. So indexing structures are trees, then the hash tables, and many other forms of the indexing structures can also be built using the DBMS facilities. Okay. So once this is all about the architecture, and we will just go to, as I told you in the first class and in the last class as well, the database is all about tables. And what these tables contain, will pay a little bit attention, is that they contain several columns. Column 1, 2, 3, 4, 5. 5 columns are there. These columns are fixed for this particular table. If the table's name is student, student has 7 columns or 7 attributes. Someone is asking, let me just look at this one. Somebody is asking, sir, buffer manager similar to the main memory? They are similar to the main memory, but they are much faster in terms of accessing the data elements than to the main memory. So in your architecture course, you must have learned the memory hierarchy. Right? At the lowest of the memory hierarchy is what elements will be there, which element can be accessed very efficiently. Yes, somebody is also saying it is a cache. That is correct. Perfect. So that is what is all about the buffer managers. So they are all caches. You are all correct. So these tables will have fixed number of columns, but they can have variable number of rows. And every column in this row must have identical data type. So for example, if SID is an integer, every record under the SID must be an integer. If name is a character string, every row under the every element under the name in these rows must be character strings. And this is a floating point number. Every row must be having a floating point number for SPA, so on and so forth. So the tables, columns are many times interchangeably called fields, attributes, columns. They are all referred to the same thing. It's a column name. The tuples, the records are all known in various names. Some may call tuples, some may call rows, some may call records. But they all refer to one entire record of the student. So if you say give me the record of the student with roll number SID, student roll number, student ID 53666, you are referring to this entire record. You are referring to the entire record. It will not give you partial records. Okay? So this is what this convention you must be familiar with. And throughout these database management systems course, all these names are used interchangeably. So you please don't confuse with the names that are used. And in theory you will see that tuples are used. In implementations you will say rows are used or records are used and so on and so forth. As I told you, the fundamental element in databases is a table. It's not a integer, not a character, not a whatever that we have in conventional languages. So these tables are what subjected to operations. I perform operations on table 1 and table 2. Just like you have performed operations on integers, just like you have performed operations on characters, or you have performed on strings, you perform operations on tables. That is what is the main thing that you must always remember. So now, these tables don't actually come with very vanilla versions. In some way, the entire efforts of the database management system is to make the data error-free as much as possible. And to do such kind of error-free data to be populated by the database, what actually tries to do is that it will place lots of constraints. Well, you cannot do this one, you cannot do that one, you should adhere to this rule, you should adhere to that rule, and so on and so forth. Even for simple table like this. And they're all called constraints. When I say constraints, it could be the constraints on the data that one record that you have populated, or constraints on several sets of records that you have populated, or constraints on the columns, or constraints on the data types that are associated with the columns. Any of these things, they all form put together constraints. And we'll see one example of what kind of constraints could be there. And you might actually feel that these are all natural. You have played with this one. I'll give you some analogies as well. That I'm not, once again, I wanted to emphasize that I'm not discussing over here all the constraints at present, but we will slowly build upon these constraints. As as far as the single table is concerned, only one table is concerned, the constraints are that there can be primary key constraint is there is uniqueness key constraint is there is not null key constraint is there is a default constraint is there, and when multiple tables are involved, foreign key constraints are there. And foreign key constraint and primary key constraints are the heart of the relational databases. And if you understand these things, you can be able to much more easily be able to adhere to the data quality that is populated with respect to these tables. That is what is the main advantage with these constraints. So we'll actually look at these things through examples. What is the primary key? We'll just kind of understand through an example that we are given a table. This table is a student's table and it contains 5 columns: student's ID or student roll number, you can say, student name, student login, student age, and the SPA. Now if I say SID, student ID or student roll number must be a primary key, what it means is that every record that you have included in this table and examine the student ID, every ID must be unique. That is what is the main meaning of this primary key. So here, the second row is a legal row. So now what is the meaning of it? These cannot actually assume duplicate values, but all other columns can assume duplicate values. It may. So I'll give you one example that here second row you please pay attention to 50,001. These two are different roll numbers, but every other attribute, every other column are identical. Other column values are identical in these two rows. Date 19 and then 8.25. So this is not violating primary key constraint. Why? Because the primary key constraint is only concerned about only the SID. It is not concerned about all other columns altogether. So second row is legal and there is no, only when there is no constraint on the login. Only when there is no constraint on the login. Assume that there is no constraint on the login, we will not even say that this is an incorrect record or incorrect database. So now where the primary key constraint gets violated. So the main aspect is that two rows cannot have identical values. So if I record with the other attributes or other terms are except SID. And this SID 53666 is over here. So it is violating primary key constraint. So this required be included into this table students. So the students table must be coming back to its original position. When you wanted to insert once again 53666 with James as the record, it should not even be inserted because it violates primary key constraint. Only when you place the constraint that SID must be primary key. I'll also give you one more example. It is that only one column can assume primary key constraint. In a table, one or more columns together assume the role of primary key. In this particular example, it is ID and then student ID, both are primary keys. What it means is that so it's a valid row. 53666 and 53666 are available. Student IDs are identical, and despite being this is a primary key, But for the entire table, the primary key is CID and student ID, course ID and student ID. Put together is the primary key. You should not look at collective. Then there is no violation. So what is the meaning of this particular thing is that one student is registering. Basics. That is what is the meaning of it. So another valid row is that two different students are registering for one course, HS105. So now the primary key constraint, what it is trying to do is that when two columns are put together to join together to play the primary constraint role, that these columns can take all possible values. So all possible values of CID cross-producted with all the possible values of CID. Only then they cannot essentially be placed together. Otherwise, the meaning is that this is the meaning that two students can register for one course, HS105, two different students. In this particular example, one student is registering for two different courses. So both are valid, and then this is the valid primary key constraint. And one more thing is that tables represent relations and relationships among rows. That is what is the main thing. And if you very carefully observe, this is what is the meaning of it. One student is registering for two courses, two students are registering for one course. These are all the relationships, one to many, many to one, many to many, and so on and so forth. So we will not go into that theory part as of today, and as of this particular few lectures. But this is what you have to keep in mind, that this is all about relations. Table represent relations, and tables also represents relationships among tables, and relationships among tables, rows also. So, and when you say relationships among tables, I will give you an example. Is that so far we have seen only one example over here, one table over here, and then one table over here. But you can actually have relations on multiple spread of tables. So here I have a table called registers, I have another table called student, I have another table called course. Now this table records all the list of students that are registered in IIT Guwahati. Say, let us say for the example. And this is the list of all the courses that are stored in this table. Course name, course ID, course name, credits, and so on and so forth. These two tables, this one and this one, seemingly independent, but they can be participating in relation through registers table. How? So this is how they will be participating. This student is registering for this course. This student is registering for this course, and that's how you are actually stating that one. Student ID is registering for this course and obtained this grade. And where is the student ID coming from? Student ID is coming from the student's table. Course ID is coming from the course table. Right? So the representation, the relations that can actually exist among tables, several tables altogether. And primary key constraint is that student ID and course ID must be primary key over here. Student ID is primary key, course ID is the primary key. Now one more example of violation of the primary key is that it may so happen that in databases it might so happen that you can say that, well, there is a special value for every column that the database can take. This is called a null value. And nulls will not actually represent any information altogether. All it will say is that I do not know what is the course number. Or it will say that, well, he has not given me the information with regard to the course number. I do not know which course he has registered, but he has got DB grade. That is what is the meaning of it. But in practice, you cannot say such kind of explanations given the snapshot of the database. And we know that it is impractical. That I do not know which course I have registered for, but I get a BB grade. This is a inconsistency in the data that is being populated. So null values are not allowed as far as the primary keys are concerned. Right? And you cannot have null key in both the columns also. See, here I have null value in the CID. Here I have null value in the student ID. I cannot allow null values in any of these places. Once again, you can have all the columns as primary key value. Right? So these observations will make a little bit more closer observation that will connect us to the actual constraint that will exist in the physical applications for which you are developing databases. This example will emphasize that one. Even though a little bit repetitive, you will understand the corner case as well. That you assume that CID and student ID are the primary key for this table, and only that these two columns are there. And these are you pay attention to the last two rows. What it means is that one student is crediting two courses, two distinct courses, and it is allowed. When I say allowed from the perspective of the primary key, that is what you have to always read. The question is that if this value and this value are repeating in the next row, only then it is not allowed. Otherwise, everything is allowed. So here at least one variation is there, that is the course ID, there is a variation. The meaning of is that one student is registering for more than one course. That is what is the meaning. Exactly opposite thing can actually happen, that one course can be offered to multiple students. Seeming like we have already discussed this one, but where this violation will come, if you mix on the constraints, I will tell you that on the same table, you have not done anything, but you have forgot to place constraint that CID and student ID put together the primary key. Let us say you have forgotten to mention that both the columns constitute primary key. What is the meaning of it is that one student is disallowed to credit for two different courses. So the moment you actually skip the primary key constraint, the meanings will completely change with respect to the real world in which you are implementing the system. So now everybody will be under panic, saying that, okay, I was able to register for HS105, but I am not able to register for HS106. That is what is the implication that will result when you misplace the constraint. Identically, reverse things can happen. That you have played a primary key constraint on the course ID, but forgot to place the primary key constraint on the student ID put together. What is the meaning of it is that you cannot allow one student to register for more than one course. Sorry. So in one course you cannot allow more than one student. That is what is the meaning. And I have to change this particular example. So for HS105, I can have only one student. And if I have one more record, HS106, HS105 and roll number is 53667, it will immediately reject it. Because, see, this example I have to modify, I will modify. So there cannot be any course, let us say HS105, which can register for more than one student. That is not allowed because HS 1 year CID course ID is a primary key, and only one student can register for one course. That is what actually happens. So what happens is that depending on the way in which you place the constraints, the meaning of the data that is populated will completely change. Right? So now I will wait for some time. I'll stop here and then receive any questions that you have. So if there are no questions, what I would emphasize or repeat is that first lab, that is on 11th January, we will not have the lab session as planned. I was hoping that I will be able to cover at least some SQL part. I was not able to do that one. So my target for you is that every one of you should install a MySQL version, latest version. Make them available up and running on your individual computers. The links are available, and we will not have any evaluation for this lab. From the next to next lab onwards, we will have that one. Any questions? If there are no questions, then we will conclude this class for today. Thank you. Thank you all.
Hello, sir.
Yes, please.
Sir, can you please stop the recording?
Yes, yes, that's correct. Thank you, thank you.